In this video, we want to see what is the relationship of if we have a linear system and a stochastic input and a stochastic output y of t. So we want to analyze linear systems interacting with stochastic random processes. So the first thing is that a deterministic system is called linear if you have this relationship. A linear system L for any input x of t gives you an output y of t, and then you may have different relationship. But we call a system linear if for all pairs of random processes x1 and x2, if you combine the two inputs, if you get two arbitrary input, if you get arbitrary input x1t and x2t, so for all arbitrary of inputs, anything they are, if I multiply the first one by any constant c, a scalar number c, and then I add them together, so this is called, what I have here is called a linear combiner, a linear combination of them. A linear combination. Okay. Now if I put my linear system here, L here, I get one output. Now I could do the other way around. I could put x1t, give it to this linear system. I could give x2t also to this linear system L, and then I could multiply these by a scalar number c, and then I add these two guys. Okay, so here I get y1t, and here I get y2t, and then here I get cy1t plus y2t. In other words, I have changed the order of linear combination and the linear system. So this is a linear system. So if I put in the first combination, I put the linear combiner here at the input. Here is the linear combination, and then I put my linear system. In the second composition, in here, I put the linear system, I apply the linear system to individual signals, and then I linearly combine them. So this is a linear combination. So if for all arbitrary pair of inputs and for all constant c's, if these two final outputs, let's say here z of t, is always equal to cy1t plus y2t, then I call this system linear. So a linear system is a system which can be displaced from this composition. So if these can be moved from this location to the inputs, if it could be applied first to the pair of the inputs separately and then linear combination applied. So if it doesn't matter if you could permutate the order of these two operation, then you call this system a linear. So linearity is a property which needs to be applicable for all arbitrary pair of inputs and all constant numbers. So if you have this property, lots of other properties are inherited. Now, a deterministic system is called time invariant. So this is one definition, and this is a totally different definition. I call a system time invariant if I have this system L, if I put a delay at the input, let's say delay of 2, if I put x of t, any arbitrary input x of t, if I put a delay here, I get x of t minus 2, and then I get, let's say, y1t. Now, if I change the order of the delay operator and the system, okay, I put this system L, and then I give x of t, and then I put a delay. And then I get y2t. Obviously, here I get another signal, let's say y of t. If for all delays 2 and for all x of t, if y1t is equal to y2t, then this system is called time invariant. In other words, a system is called time invariant if it doesn't matter if you put the delay first and then your system, or if you put your system first and your delay. In other words, in time invariant systems, you could take the delay from input to the output or vice versa. In linear systems, you could interchange the order of linear combination and your system. In time invariant system, you could interchange the order of delay operator. So here is a combination linear combiner operator, the order could be changed. In time invariant system, the order of the delay and the system. So if you have two properties, then you call your system linear and time invariant. In some system you are only linear, in some other system you are only time invariant. So remember, mathematically, time invariant system, we say a system is time invariant if the output of a system to x1t is equal to, if you apply any delay to your system, so here you have only one input, if you impose a delay to your input, you observe the same delay at the output. So it doesn't matter. So this is the math definition, and I have pictured it for you. And this is also the math definition for a linear system. So having these two properties together reduces the class of systems which are both linear and time invariant. So let's say this is the space of all linear systems, and this is the space of all time invariant system. In the intersection of them, these systems are called LTI, which are both linear and time invariant, and they have very interesting property for which the output can be written as a convolution of the input with something which we call it unit impulse response. So a linear time invariant system is characterized by the impulse response. So the output, if you have both linearity and time invariance, that means that you are at the intersection of both these two systems, then the output can be written in this form. So that means that for any linear time invariant system, there exists h of t such that the output is equal to this one, and this is an integral. So this is an interesting property which we use in order to characterize if this h of t is deterministic and this is a stochastic process. We could fully characterize the output or autocorrelation of the output, input, or any other moments or distribution of x of t, y of t, joint distribution, and so on. For example, if you have any linear time invariant system which is also stable, we say a system is stable if it is h of t integral of these from minus infinity dt is a finite number. So if you have an LTI system which is stable, and if input is normal, the output also shall be normal. Sometimes we use this as a definition, but here you can use it as a theorem exercise. Using this integral, prove that the output should be always a normal random process. For instance, if the input is y-sense stationary and normal, the output also should be y-sense stationary and normal. Moreover, if x of t is a strictly sense stationary, y of t should be also y-sense stationary. Sorry, a strictly sense stationary. Or if the input is a strictly y-sense stationary, y of t should be always y-sense stationary. Okay, so for any LTI system, if you have LTI, if this x of t is WSS, you could immediately say that y of t should be y-sense stationary. Not only that, but also the pair of x of t and y of t, they are jointly y-sense stationary. Or if the input is only a strictly sense stationary, the input and output, the pair of input and output are also jointly strictly sense stationary. Another case was that, the first one, if the input is normal, the output also shall be normal. If the input is stationary in any sense, this stationarity will be inherited to some of the statistics of the output. Because if something is not changing in the input, this system is not changing with time, so something else should remain unchanged at the output.